Hi, this is Animesh Singh. I'm a director at LinkedIn, leading a GPU fleet and infrastructure for training and inferencing. In addition, I lead the distributed training software stack across all of LinkedIn. Additionally, contributing to and leading a lot of initiatives around ML efficiency and performance optimizations. Prior to that, I was a distinguished engineer and senior director at IBM, leading a lot of core Watson initiatives.
Woo! I'm bubbling from this conversation. So many gems when it comes to working with LLMs at scale, GPU infrastructure, what you want to be optimizing for, how you can think about optimizations. And I had a incredible question at the end, like how does the platform and the GPU infrastructure that you're dealing with differ when it comes to working on LLMs versus traditional ML? Did not disappoint. Let's get into the conversation. Well, let's start with this, man. And I'm so happy that we got to do this because we've been jiggling around our calendars to make this work for probably about 6 months. I think we were going to do this when I was last in San Francisco in June, but one thing led to another. And here we are in 2025 having the conversation finally. Persistence paid off.
I think this is great, and I've been following your work throughout as well. You're doing excellent work in terms of bringing communities together and disseminating that knowledge, right? Like what's all happening in the AI space, right? And what use cases are springing up. What are the industries they are targeting? There is some excellent work you are driving in that, and I'm so glad it's happening in 2025. We have now some better experience of what is working, what is not working, what may be a little bit of the hype, right? What is realistic, what is going to be the trends in 2025. So I think the timing is working out. Yeah,
What is working?
one thing which has definitely proven that it's here to stay is LLMs, right? I feel throughout, um, 20, 22, 23, there was lot of, discussions how effective LLMs are going to be, right, in the industry, in the space. There are a bunch of, modeling architectures like, recommendation ranking, LPMs, graph neural networks, GNS, right? But the efficacy of LLMs and the use cases being powered by LLMs was quite a bit of question mark, right? Like, yes, there was a promise. What we saw, that magic moment with ChatGPT coming in, that literally, woke everyone up, right? Hey, it does seem seamless. It does seem that it's not yet another chatbot you are talking to, and that sprung up the industry, right? When I joined LinkedIn at that time, the ChatGPT moment hasn't happened, and as soon as I joined a month later, ChatGPT came in, and what I came in here to do, a lot of that changed within a period of a month. And I think through the course of that period, multiple companies, multiple industries have identified, right, different use cases which are working well with this, right, and people are being productive. Uh, be it either generating code, be it able to do certain automation, leveraging this. The interface does seem very human like, and a lot of the generative AI use cases which we launched even on LinkedIn, for example, profile summarization, right? So based on what you have, create a headline for me, create a summary for me. Use cases like assistant for LinkedIn learning courses, use cases like resume targeting recruiter emails for candidates, because a lot of the things which we had seen, that if you're getting cold call emails from recruiters, they are not hyper personalized, right? Like at times they sound like a template. Generative AI and LLMs helped us immensely in that, right? Where they take into account the candidate's profile, the company in which candidate is working, the company from which the recruiter is, and create these very personalized emails, which, we are seeing success candidates actually responding much more, opening those emails. So I think, bunch of use cases we have seen working really well with LLMs, and we are obviously doubling down, right? Like if you see the talk of 2025 and even before that, last year there was quite a bit of discussion on agents, what they can do, what they cannot do, and we did our own experiments, right? Like invested a lot internally in terms of building agent infrastructure, right? First of all, right, what does it take to create agents? How is it different than the traditional generative AI applications or use cases we were building? What are the nuances, right? What makes it different? And then finally, we launched, closer in the last quarter of last year, LinkedIn Hiring Assistant, right? So, which is essentially an agent for the recruiters, which based on certain criteria they define will actually go work behind the scenes, find candidates for them, relevant candidates, summarize their experience and profile to the recruiters, and then based on that they can tell, okay, you know reach out to these particular candidates, and let's start having a discussion. And there is much more. We are doubling down on that whole LinkedIn Hiring Assistant, and we have seen some great enthusiasm from our partners and customers, right? So it's seeing some very good results. So there is much more we are doing now on other areas of LinkedIn, which will be powered by agents. So they are here to stay. I think it's how in which use cases really benefit from it. That will be a nuanced discussion. You cannot throw it at every single thing. There are so many things which can be just powered by them, which then frees you up to do things, right, which are probably the more creative aspects of the work you are doing, right? And we are seeing quite a bit of that happening.
So what's not working?
I wouldn't say what's not working, but a thing which probably needs a lot of improvement moving forward is the cost and the ROI of launching these LLM based either agentic use cases or traditional, prescriptive RAG based generative AI apps, or even, leveraging LLMs for use cases beyond generative AI. The cost is a big hindrance. I think one, if you see, like, training itself used to be the biggest barrier for entry, and that got solved to some extent because, first of all, even within LinkedIn, we invested quite heavily in building out or scale out training infrastructure which can power LLMs. I think when I came in, we were working off a V100 fleet, and then since then we have scaled our LinkedIn fleet by 7x. We have A100s, we have H100s, we have H200s, and the fleet is as modern as it could be, and we have scaled our training tremendously, right? Like, it's 150x increase in the size of the models we are training, right? Our data processing has increased manifold. We actually, completed 1 million training runs on the platform, and training big foundation models. Now, investment in the infrastructure went in, and I think it was well understood for companies at scale of LinkedIn, etc., right, where a lot of content-based data is being consumed, being produced. You will have tons of data, right? And when you have these tons of data, you need to make sure that you have the infrastructure to train models on these data, right? And then the other thing which actually helped a lot of the training landscape is the emergence of open source models. I think Meta led the way, followed by many others in the industry, right? Where for smaller companies or for companies which there is not a need to train a model on world data, right? Like, you have your own specific data which is probably not as big as the world data. Getting these open source models and starting on top of them, because these models already know what exists in the world. They can answer your questions around, they've crawled through Wikipedia, they've crawled through, public libraries. all the articles, and they're being trained on them. Then you can bring in and do more fine tuning instead of, training on huge amounts of data. So then the infrastructure cost can go down further, right? So fine tuning became a big mechanism. Plus, the emergence in the industry around a lot of techniques around supervised fine tuning, zero shot, few shot learning, which emerged, where, prompt optimization techniques which emerged, which essentially brought the cost down heavily on the training side. What is now, more and much more in the picture is the cost of inferencing, right?
Mm.
And I think it's humongous, it's big, and there are a lot of efforts, right, which we are doing, which the industry is also doing, right, overall, how to bring down the cost of inferencing these models. Now, if you take a look at um, generative AI use cases specifically as well, there is some thinking which is built in, like when you are interacting with a model, right, where you are asking certain queries, asking it to analyze, you are prepared mentally. It will take some time, it will think through it, right? Even with the emergence of, the latest OpenAI models, right, where there is a lot of reasoning going on, right? So there is a lot of, it is actually analyzing its own output, then, refining its own output, then the second output is further analyzed. There is a lot of back and forth reasoning, so there are multiple inferencing calls happening. And I think as a consumer, we are prepared. If we are going into a scenario in this particular context, the model may have some thinking time, specifically if you are interacting with the latest OpenAI models, etc. Then you know that, you're asking complex queries which need that analysis. So the latency you are willing to tolerate. Now the adamant, and even to get to that latency, right, like there's tons of infrastructure investment which has been made, right? The general realization is that, with even with all these investments, we are not able to get our GPUs to perform at maximum utilization, right? Like inferencing is becoming very costly because you are optimizing a lot for latency, throughput, and you have a lot of failover mechanisms which you need to build. Like almost any company needs to account for, hey, I have two or three data centers, right? Like if one data center goes down, so there is a lot of redundancy you need to build for applications which are user facing. That means, the cost of GPUs is ballooning, right? And that's essentially is an infrastructure problem which needs to be solved. Specifically now, when we do take LLMs in use cases where the consumer appetite for latency might not be there at all, right? Like there are efforts happening across the industry, right? Like, hey, the traditional Rexis, right, recommendation ranking. Like, so for example, you go to social media sites, you get recommendations, you get feed, you get people you want to connect with, all these things. Like, as soon as you go to the site, this should be there, right? You should be, as you're scrolling through the feed should be just being, updated and customized for you in real time. There is no appetite for latency in those scenarios. Now, if you need to uh, see if LLMs can be effective in those world, that means, you really need to optimize for latency. And if you're really doing that, you are potentially throwing more money at the problem. And so that problem, I think, how do we take this large language model architecture, the transformer architecture, and make it really, really optimized for inferencing, right? Is becoming a big thing, right? Which needs to be solved for scale, right?
Do you feel like it's a bit of trying to fit a round peg in a square hole because when you throw LLMs at like a Rexis problem, just because we've been doing Rexis for a while and we figured out how to make it real time. Why do we need to add an LLM on top of it? It almost, in my eyes, is overcomplicating things just to try and use a shiny new tool. But maybe you've seen there's better performance, there's better personalization there, or something that I haven't.
I think I would, more than speaking on my behalf, right? Like in general, there are, like, research papers emerging, companies are trying that. Now, why would you try something like that, right? I mean, and that's a fair question, right? Like Rexis is already well established, right? And as a architectural pattern, right? Like the traditional recommendation ranking models, retrieval models, including something like graph neural networks and GNNs, etc. Right? They do a very very solid job at this, and you have
Yeah.
seen
And it's
companies
fast.
like
And it's fast.
it's fast, and uh, like you take a look at TikTok. Oftentimes, the recommendation algorithm is talked about. So you're fairly right. Like, hey, is why is that why? I think there are couple of things in heuristic, right? So the way we have solved recommendation ranking problems in the industry is obviously you have created models. A lot of the companies have smaller models, right? These are not traditional foundation models which have been trained on world data, etc., right? They have potentially not seen a lot of user interactions and patterns. So then, you add things like real time training. There is a lot of data being ingested in real time. Online training is happening. There is a lot of feature ingestion which is happening in real time. What is user interacting with? So there is this new paradigm, okay, which is these models, the LLM models, these are foundation models. They have potentially seen maybe 95% of the patterns. So maybe the what you need to do in real time to update these models is probably a lesser investment, right? Models have seen majority of the patterns, and if you feed what the user is done, right, like they would be able to predict much more comprehensively. You don't need to do a lot of online training, etc., right, in real time. That's one of the thinking. The other thing is the simplification of the architecture. um for something like GNNs, right, what we need to do is, when you are doing the training, GNNs, all the data is in the graph format, graph structure format, right? You need to traverse the nodes and the edges in real time, right? Because you don't know pre-hand, right? Like how much data you will be processing, which will be the right node, which edge you need to traverse, right? So there is not data pre-processing happening. And there is a different architecture, and it's inherently hard to scale GNNs beyond a certain limit because there is live data processing happening while the training is going on or while inferencing is going on, right? So, an architecture, and then JNN is one example. There are different, recommendation ranking architectures, and then companies would have a proliferation of these recommendation ranking models, right? Like every team would create for each of their use cases. They would start from scratch and create a model which is potentially small model. It does very targeted job. It does a really good job at it, right? And then build all these things. So you have bespoke models with different architectures. There are huge number of them. If you take the LLM route, right? Like the trend which is emerging in the industry, right? Hey, if I do create a giant foundation model, right? And if you're obviously very present in what's happening, distillation as a technique is becoming very prominent in the industry, right? Like
Commonplace.
I
Yeah.
will create smaller models for inferencing, but I will distill it from this giant foundation model. So what you have done is, you have sort of centralized the creation of models in potentially a central place. So you can think of a scenario in future, right? Like there is one central team instead of having every different use case and every different vertical within your org creating their own models for their own use cases, which are very targeted. One central team, which is, the holder of your organization's data, which is curating that whole data and creating, maybe one or two or three. Okay, very simplistic scenario. You're creating two giant foundation models, one for generative AI use cases, one for non-generative AI use cases. And then, the models for all particular use cases are being distilled from this. So you have simplified the overall architecture. You are essentially worrying about the compliance majorly. Like there is compliance is a big thing as well, as you are seeing, right? There was the DMA Act, there is AI Act, there will be other acts
Yeah.
which will be coming. If you curtail the surface area, how many models you have, right? What data it was trained on, right? Then you're not worrying about the uh, many hundred other models which your organization has created and make sure everyone is compliant. What data it was trained on, was that data compliant? You have sort of centralized and simplified that problem. Hiring becomes easy, right now you do tend to hire, like when I'm looking at certain use cases, like GNNs, people who can run GNN at scale, right? You need a very targeted skill set, people who understand, how to target graph data, and then you need to go into the depths of the GPU's architecture, where is because what a lot of data transfer is happening during that training. So, okay, is NVLink good enough? How much HBM memory I have? How much on-disk memory I have on the GPU nodes? Then, what is the network bandwidth? There is a lot of in-depth GPU knowledge you will require, right, just to go there and start solving. Plus, the graph traversal, what algorithms do I need to introduce to? So your sourcing of skills and talent also becomes simplified. So there is that overall value proposition which could be achieved, provided if LLMs do um, prove themselves. I think many are looking at this problem space and figuring that out. So it's yet not solved. And as I said, like, unlike uh, generative AI as well, this is a problem of scale. Like generative AI use cases, you have to explicitly, as a user, go and invoke that, right? You will go, like, I'm giving you LinkedIn example, right? You will go and say, hey, summarize my profile, or a recruiter will say, launch this particular agent, or LinkedIn Learning user will go and say, summarize this course for me, or explain to me this nuance. So these are, discrete transactions. Users going to feed, logging into feed, browsing through the content. This is happening all the time. It is happening at scale, right? So then that's a much bigger scale problem which needs to be solved with um, LLMs overall, right, in a cost effective manner. I think it's and very, very, latency sensitive manner. So that's the thing, right, which needs to be happening, and we'll see whether they do prove efficacy. Like, based on all the results you see, they're able to pass a lot of bar exams, PhD exams, math exams, right? So you see, hey, they are intelligent, right? Like, can they be very intelligent for this specific set of targeted problems? Yeah.
I hadn't thought about the simplicity in the architecture and also the simplicity in being able to attract talent that understands this architecture because it is more simplified. And you were talking about the cost of having GPUs at scale, and when you have this many GPUs and you're trying to utilize them, you don't wanna have any percentage going idle. I imagine you think about that a lot. You're thinking, "Wow, we're burning money just letting this GPU sit around, and we're not utilizing it to its maximum capacity." Is that what you're trying to do, or is that what, Liger kernels are trying to help out with? Can you explain that?
Any infra and platform team which is in ML infra at this point, you will talk. This is a burning uh, thing, right?
Keeps you
Which
up at night.
you have, on one hand, you cannot run these LLMs, for example, or these modern recommendation ranking models without GPUs, right? Uh, Training, definitely, right? And even with inferencing now with LLMs, you have to go on GPUs, right? Like the general trend in the industry, like if you rewind 2 years ago, was, hey, we will train on GPUs, would serve on CPUs, right? That's how most of the companies had architected, and CPUs were not that expensive. The modern architecture, it doesn't lend you to that, right? So you need to get, so the whole investment in GPU efficiency becomes very, very paramount, and it starts from at every single layer. Like in our case, like, okay, there is the general thing, right, which also happens in companies, right? Hey, you need to allocate a maintenance budget. Now you can be much more generous with CPUs, right, in terms of maintenance budgets. How much spare capacity do you allocate, so that if your 20% of your fleet is being maintained on a regular basis, so that's the delta you need. If you need high availability, you need to spread it across 3 data centers. Okay, let's go ahead and do it, right? Those decisions were much easier. They're becoming much more harder when you have GPUs in house, because yes, there are certain companies which have potentially invested a lot, right? And they have deep coffers, but a lot of the companies want to be cost conscious about it, right? Like you are, so every decision, hey, even to the point, like looking at certain use cases, what would be the right maintenance budget, right? Like if you have let's say, in one maintenance zone, 1,000 GPUs, can I allocate 100 just for maintenance, right? Like then you do the cost and it's like, hey, there's a lot of wastage which is going on.
You
So how
start
do
sweating.
you
You
start
start
sweating?
thinking about how much money that is, and
Yeah.
wow.
And so how do you first of all start then looking at the workload so that they become more resilient to maintenance? Like, so okay, if I cannot take the previous approach used to be like, once I know 20% of my fleet is going to be maintained, I will not schedule anything, right? We don't need to worry too much about, for the next 24 hours, even if they're empty. Now you're worrying about that. I cannot leave 200 GPUs lying empty for 24 hours, right? Just because, the maintenance is going to happen. So then you look at your workload. Okay, how can I make the workloads more resilient? Now, if you look at distributed training workloads, right? Majority in the industry are gang scheduled, right? So you do gang scheduling, beforehand, this distributed training workload will take X amount of GPUs, right? And there is a lot of, synchronization happening as the distributed training is going on. And if you know uh, few of the nodes fail, you will have to put it back in the queue. Like you obviously need to have checkpoint restore, put it back in the queue, do again gang scheduling, so that it can resume. So then you look at this workload. Okay, maybe in this world we have to rethink the whole notion of gang scheduling, right? uh, do we need to build more elasticity, right? Like if a workload has been launched on 100 GPUs and 30 GPUs are going to be taken away, can it shrink, can it expand on its own, right, and continue going? Same for inferencing. I think the need for scale down, scale up is becoming big. Serverless architecture has to become a prominent scheme in the thing of things. Like you cannot optimize for max traffic. Like, and a lot of us are doing that. A lot of the industry is doing that, where you put what is the peak traffic you get, and that's your capacity. But if out of 24 hours, 2 hours is your peak traffic, for those rest of the 22 hours, these GPUs are sitting idle because they have been provisioned to handle that peak traffic. Again, a lot of wastage. So
Yeah.
many of these decisions are now becoming very prominent. So I feel the emergence of elastic architecture, serverless architecture to handle workloads which should be able to scale down, scale up as the capacity is, shrinking, expanding, is a big investment area, and something, right, which uh, we are doing, like, and I'm assuming, like, a lot of people are solving this problem at different means and mechanisms, right? So yeah, that's essentially the key characteristic there.
Well, and you haven't even mentioned the reliability of the GPUs because they're notoriously unreliable.
They are, like, there are, I mean, all these NVIDIA GPUs you get, for example, right? And one of the decisions we took uh, early on, and I think for the simplicity part of it, right? Like, hey, let's start at least on the training side, right? We'll go with NVIDIA. And so far, we have standardized on NVIDIA throughout, but then, you have a lot of these checks. Things which can go wrong, because, like, just taking a distributed training example, when you are running at scale, you are touching your in our case, we have Kubernetes as the compute infra layer, right? So you have Kubernetes, you have the network, you have the hardware, you have the storage. Training is, reading and pumping a lot of data throughout. Any of these points going down is a weak link, in addition to the GPUs itself, right? uh, and add to it the planned maintenance. And sometimes, for foundation models, your training can run for 1 week, 2 week, 3 week at stretch, right? When you are actually running training for these large foundation models, you're guaranteed to have some part of the infrastructure having some problem. Sometimes it will be the messaging queue, sometimes it will be the storage system, sometimes it's the something in the
Memory.
Kubernetes layer, or sometimes it could be just the GPU node itself failing health checks, ECC errors. Nickel is a problem, InfiniBand of the GPUs, right, which is connecting all this. So this poses a huge challenge, right, in terms of ensuring, because these are so long running jobs, how do you make sure that you are being effective, right? And that combined with the problem of gang scheduling, because hey, they need to go all together at once, or otherwise they will need to wait. If a training job needs 500 GPUs, it will be in the queue until those 500 GPUs are free, right? You cannot launch it
Yeah.
before that because you have not. I mean, that's how the architectures around gang scheduling are built. So this is a big thing, right? Which we have invested a lot in terms of building, very fast checkpointing restore, because you assume failure is happening, maintenance is happening. So a lot of investment has gone in from our side in terms of ensuring that there is automated checkpointing restore which could be done, and which is hierarchical. So we first checkpoint in memory, then distribute those checkpoints to some async block storage, then you have to read, right? And then there is also discussions around whether these checkpoints can reside on the GPU SSDs itself, because there is a cost of reading. Once you have, like, the training can continue checkpointing in memory, but once you have sent it to some remote storage, a block storage or a file-based storage, then when you're reading, if something has gone wrong, that takes time. You have to bring that
So
through the
long, right?
network, and
Yeah.
bigger models will have many gigabytes of checkpoints, right? Bringing them through the network. So then, okay, can we leverage the GPU SSDs under the covers itself, right? GPU SSDs obviously have some limited capacity. How much can you store? So bunch of those architectural elements need to be crafted. So we are investing quite a lot and quite heavily into that. Liger, you talked about, right, was the other part of the efficiency problem, right? Which is essentially, as we went on this journey, we saw, like, beyond the reliability and the scalability, a lot of the use cases as the model started getting more complex, more bigger, and we had an X amount of GPU fleet. We started seeing a lot of pulls from our customer. Hey, I need GPUs, I'm not getting GPUs, or my training
Yeah.
is running for, like, so long, right? And I really want to get it done faster. Multiple of these use cases, and literally people were uh, because GPUs was our scarce entity. At least a year ago, we had quite a bit of that, right? We were scaling the fleet, right, and we were ordering. Nvidia has its own supply chain and timeline, right? The use cases were just springing up. So we looked at the problem, okay, and you follow the traditional methodology of data parallelism, model parallelism. Let's introduce tensor parallelism. We invested in technologies like zero plus plus, because our A100 fleet had very constrained network bandwidth. So how you can scale up training, even with that constrained bandwidth, zero plus plus helped in that. So after we have exhausted every single option, then okay, what can we do? So as we started going deeper, one of the things which we used to do infrequently for our customers was, rewriting CUDA kernels. Right, like a lot of the use cases which are very sensitive to that the training should complete within X number of hours, etc. When we looked at the model training code, which our models used to produce, there was a lot of improvements. So at times we will go and rewrite the CUDA kernels, few certain operations, right? Now you bring this to the LLM. The thought which we had was, hey, we can do this on a model by model basis, but this is not scalable, right? Like there are multiple users having different models. So the thought, okay, how can we make what exists to actually solve this problem, which can be a little bit more scalable? So that's where, fortunately at that point, OpenAI has launched Triton, which was essentially a Pythonic programming interface, right, where you can do CUDA kernel programming at a much abstracted layer. Most of our users would be, familiar with Python. So using that, now the second thing was, like, GPU memory is hierarchical, right? Like you have the DRAM, then you have the HBM memory, then you have SRAM. The streaming multiprocessor, SSMs and GPUs, they interact mostly with SRAM, right? Which is very little. So every time, and so all these multiple kernels you have and multiple operators you have in your training code, there's a lot of data transfer happening, right, from CPU to HBM to SRAM. Like that is your biggest bottleneck, right? Even though the GPUs can massively parallelize, the amount of IO, data IO, which is happening between different hierarchies of memory, that's becoming a big bottleneck for the training time. So that's when we thought, okay, let's combine what Triton is brought to the table. Let's take this problem and create certain, first of all, custom kernels for our distributed training workloads. And we started seeing huge gains, right? Like in one of the cases, like just 300% increase in the overall efficiency. Majority of the cases, like more than 50% decrease in the memory which was being used. What we did was we started fusing kernels, right? Like certain operations, they can be just combined, fused together. Operators can be fused together. You don't need to have five kernels to do these different five different operators, right? And there is some human judgment involved in that to make that decision. Which and we have also seen flash attention in the industry sort of solve that quite a bit, right? And it became very popular, and it was built on the principles of kernel fusion. So we took that and combined that, and it solved and helped immensely a lot of our internal developers. Huge decrease in training time because memory efficiency got much bigger. And once we realized, hey, this looks good, and let's just open sources. There was not a lot of planning. There was not a lot of thought. It was also like, hey, lot of open source models are coming in, and maybe if community likes it, they will potentially create kernels for those open source models, and if we end up consuming it, it eventually also benefits us, right?
Yeah.
It just took off, right? I think multiple companies were in the same position, right? It's when you like go and put a problem out, they were all getting this big load of generative AI use cases, a lot of LLMs, GPU crunch was omnipresent, and almost everybody, right, needed to solve this problem for distributed training, right, at scale. And we got a solid reception, right, in the community, right, from Andre, Hugging Face. We One thing which we did spend some time on making the use very easy, right? So we integrated with the Hugging Face ecosystem right off the bat, right, etc. So, and we just last week it completed more than 1 million downloads, right?
Incredible.
This is amazing. Like we never thought, this will go all the way there, right? So, and we have gotten lots of good feedback from the users who are benefiting from it.
Yeah, it's funny that you mentioned the memory aspect because we had a guest on here a few months ago talking about how his whole thesis was that we are memory constrained. We're not GPU constrained. GPU is almost like not the way to look at it. It should be really looking at memory. And that is the bottleneck right now.
And I think very rightly so, right? Like, see, ultimately, ML is a data processing problem, right? Now, so that does mean that, there's a lot of data moving in between these GPUs, right? Now, the fastest you can process data is if the data is in the memory, right? Now you go through the hierarchical thing, okay, GPU, HBM, SRAM. The second thing is, okay, the CPU on system memory of the CPU on the GPU nodes. Then you go, okay, I will go outside the GPU nodes, right? Maybe the GPU SSDs, right, itself. But the more you can keep in memory, the faster you can process.
Yeah.
More so for uh, LLM oriented workloads, generative AI workloads, because if you look at, people want to have bigger context length, right? Even when you are training the model, right? If you increase the context length, you potentially can train bigger models. Inferencing time, right? Like the amount of information users are sending, right, for the model to process, the amount of information the models are generating. Like, see, Rexis output used to be very straightforward, right? Like it's Rexis recommends you whether this is a good content to show or not. In case of generative AI, the output is also huge, right? So a lot of that data processing is going back and forth, and the more you can, leverage the memory effectively, the biggest gain you can get. So it's rightly so. There is a lot of even during inferencing time, like KV cache is becoming a big technique, right? Like where you can reuse KV cache as the inferencing calls are coming, right? For sequence of tokens, etc., right? Which we have seen before. You
Yeah.
calculated
That can
attention.
save a lot of costs too. Yeah.
Yeah, you've already calculated attention scores for all these different, tokens you are seeing, the sequences you are seeing, right? So why do this again? So let's keep it in memory. But how much can you keep in memory? The other part is like, if you start leveraging GPU memory for KV caching, then model itself needs GPU memory for its own processing. So what is that right boundary? Uh, and most of the H100s, right, which is now dominantly like if you look at what the uh, industry has, probably most in bulk is right now H100s, right, or to some extent H200s, and 80 gig memory per GPU is turning out to be low, right, based on the amount of data you're processing. And I think part of it is also as the use cases emerge, that starts becoming clearer, because the way maybe the whatever went into the decision making was, hey, this memory is for GPU processing, whatever GPU is computing. When people start leveraging this memory as a cache, like KV cache, like in case of GNNs, also we are keeping some part of the graph structure in memory. When you start using it as a data storage mechanism, in addition to being used for computing needs of your model itself, then it's less. Then you need more. So
Yeah.
I'm assuming the that uh, realization is already, like, if you see the Grace Hopper architecture and the Grace Blackwell architecture, where they're combining ARM CPUs with the GPU nodes, and then they're creating a very high bandwidth data transfer link between that, the CPU and the GPU, so that you can then leverage the more memory on the other side of the CPU nodes, because there is a very high bandwidth data transfer. Or realization to this particular use case, which is emerging from generative AI, right? It's yeah.
I want to give a shout out to the person who said that to me because I was trying to remember their name. It was Bernie Wu was the one who said that we are memory constrained, and you just went very deep in that and makes a lot of sense, everything that you're saying. You did mention one thing that you worked on quite heavily too, which I've also heard is an absolute pain around checkpoints and speeding up the checkpoints because A, it's not clear when things are gonna fail, so you don't know if you need to checkpoint every second or every 5 seconds or every 5 minutes or every day, and so you if you over optimize for checkpointing all the time, then you're potentially transferring around a ton of data, and you don't need to be, because as you mentioned, these checkpoints are huge. And so, especially when you're training LLMs that are very, very big, the checkpoints can be in the terabytes. And that's just like, if you're doing that every 5 seconds, that's a whole lot of data that's going around. So, how did you specifically speed up the checkpoint and make that process better?
I think we decided, like, so initially the very naive implementation of checkpointing was, so our majority of our data is on HDFS, right? And we will the mechanism was, you checkpoint and the checkpoint goes to SDFS, and when you're reading, right, you read from there. So the realization specifically, yes, with LLMs, like, first of all, these checkpoints are big, and the training pauses while you are checkpointing, right? So there is a pause in the training workload, and this gets done. There's a transaction which is happening, right? So the first thing which we did, and changed that architecture as LLMs became more prominent, is, hey, let's make it, two-phase transaction, right? In essence, we will checkpoint in memory, right? So and from there onwards, any copy of that checkpoint is a sync. So 2 points, right? Like, the checkpointing in memory is very fast, and the second thing is, you're not waiting for that checkpoint to be transferred to a remote storage, right? So it's hierarchical checkpointing strategy which we developed, and now we are, streaming that checkpoint. We also changed our backend for checkpointing storage from HDFS to a block-based storage. Now we are, investing in figuring out, going and optimizing it even further. So GPUs, if you request, like when you are ordering GPUs, NVIDIA GPUs, you can request SSD storage within the GPUs, right? Uh, and there are technologies which I'm assuming, some of the companies may have in-house, but even in open source, right, where you can then start looking at creating a cache, a distributed cache onto the GPU SSD. So maybe one GPU SSD storage is not enough, right? It's um, for your needs. Then you can combine the GPU SSD storage across all your GPUs and then create a distributed cache to store this, right? So that's the second phase we are on in terms of ensuring so that even and the advantage with that will be in the restore. I think checkpointing will still be fast because it's in memory. It's then will go to the GPU SSDs, but when you are reading back, if you don't have to take it outside of the GPU network and bring it back into the GPU network, you save tons while restoring and when reading. The other thing which we did was, like, to your point, one of the questions was how often do you checkpoint, right? I mean, that's a big question. And we have mostly uh sort of, left it to the modelers, like, to take that common sense decision. How soon should you checkpoint, right? How much of a, like, for example, for jobs which take like more than a week to train, I think they can have a, hey, how much I'm willing to lose. I'm willing to lose 5 hours worth of data, or am I willing to lose, if something goes wrong and I have to restart, can I restart from previous day's checkpoint? So it's a decision making, right, heuristic in certain use cases, like very deterministic use cases. When you're doing incremental training, like you need to train every few hours, then it is very clear, like, hey, it's driven by checkpoints, right? So you have to do a checkpoint, every 2 hours, etc. So depending on the use cases, the other thing which we have done is like disruption readiness. So if in cases of planned maintenance, right, where we know that the nodes are going to go down, right, we trigger a checkpoint, right? So it's a triggered checkpoint. And if the modelers have implemented checkpointing restore, right, that trigger will go invoke a checkpointing restore. So this is not a plan. This is not, it's happening before we take that workload off those nodes, right? So essentially, this is signal from the underlying infra that, hey, these nodes are going away. I'm triggering a notification, this notification, and this is all automated right now. We'll go to the model, running model, that will be checkpointed, moved, and then, we will put it back. And then we are invested in things like priority queuing. So if things which are being disrupted, they should be moved to the front of the queue, like a Disney front of the line pass, and rescheduled like as fast as possible, right? So you need to invest in those mechanisms to make sure that, that goes on smoothly. Yeah.
I like the idea of, first of all, just getting the checkpoint offloaded as quickly as possible so you can get back to training and then do what you want with the checkpoint, but don't have everything stopped because you're trying to offload the checkpoint. So like make that as quick as possible. I think I've heard that before as a design pattern. And then also make sure that there's no surprises for the model that is training. And then it's like, hey, what happened? I thought I had all this resources and it all went offline. So you make sure that these things are that they feel kind of standard, but it's like, unless you think through it or you have a bad experience, I imagine you probably had an experience where you realized, wow, we should probably do something about that because there was a whole training job that just kind of went to nothing. And we could probably provision or at least put a bit more anticipation in place for that. One thing that I was thinking about is how we've been centering this conversation a lot on the new paradigm of LLMs and agents, but LinkedIn still has a ton of traditional ML use cases, right? So, how do you think about bridging the gap or creating a platform that can service both the LLM, the agent use cases, and then also the traditional ML use cases?
I think it's happening. So certain things are common, right? Like obviously all the investments we are doing in the GPU infrastructure, GPU monitoring, observability, resiliency, um, and, building things like distributed checkpointing, restore, automated disruption readiness. Then, it goes. Then you start going into, like, so one of the things which I did once I came here was, we took a major decision to rehaul our machine learning training pipelines. The pipelines or the orchestration engine was built very much in a solid prescriptive way, right? Like it was multiple components which we had in our training pipeline. It was built on TensorFlow, and sort of, it's a similar paradigm which TFX follows, TensorFlow extended. You look at from Google, and then every single step is sending metadata to the subsystem, so very rigid. Now I think that realization was very early on. Hey, this uh and part of this was also, there is a lot of traditional feature engineering which happens with the traditional Rexis models, right? As opposed to LLMs, which don't have the notion of feature engineering. You are feeding, gobbles of text. So the feature engineering as a discipline is sort of disappearing in this new world. And there is a lot of new RAG based architectures which are bringing up, right? You're doing more in real time. So the machine learning pipelines engine, we rewrote and we redesigned on an open source orchestration engine called Flight, because the notion was that experiments will be very heavy, right, in this new world. And so, there is a lot of quick changing of code. I want to do very short fine tuning jobs, or sometimes very long running jobs, but the user experience has to be very nifty. We launched something called interactive dev, where you can, have a VS Code connect to a remote running job, right, and put debug pointers and trace through what is going wrong, because otherwise the previous experience used to be like, you don't know what has gone wrong. So once it has gone wrong, you need to rebuild, recompile, re-upload. So this whole new modern pipeline training architecture, which is very much focused on very quick changes, very much experiments, you don't need to re-upload, go directly debug there, see what values are being passed in real time through your debug pointers, go one by one. And then, once we standardized LLMs on it, we are migrating a lot of our traditional Rexis models onto this new platform as well. And the feedback from users is really great. Like they're all liking this a little bit less rigid, very experimentation oriented architecture, where the back and forth things which they need to change, right, to change their model and train their model is and there is a very inbuilt robust versioning mechanism. One thing which was missing in our previous versions of machine learning pipelines was, you have a config, you have a model, you have a data set, all these are different version things, right? And you do an experiment, then you have to go and look at every different entity, what was correlated with this particular experiment or training run. So in this new machine learning pipeline, right, there is a very, very robust versioning, right? Like in terms of all the entities, your configuration parameters, your pipeline, your model, as well as what data version, these are all bundled together, right? So every experiment is associated with the right lineage. Like, okay, this was all the things which were used to create this particular model, right? So versioning is very robust, because it's sort of built with that assumption you will experiment a lot, right? So that's one change. I think one thing which potentially, and again, it's early days of the what will change in Rexis vis-a-vis the non-LLM architecture. I think the LLM architecture itself, like one hypothesis is, hey, the LLM architecture itself will take place in Rexis, right? So then, okay, whatever you have done at upper layers, right, for, or you're doing for LLMs like vector DBs, embeddings, right, they become the prominent mechanism. Overall, the RAG becomes a prominent mechanism, right? So your traditional feature engineering pipelines, the way you were constructing, they will change. The real-time feature pipelines, not the offline, right? They will change to accommodate to this new paradigm. Tools like LangChain, LangGraph, which are very much dominant in the LLM space, they may become prominent in that space as well. So far, we haven't gone that far. I don't think we have looked at, hey, can the how the LangChain or LangGraph is being used, right, for LLMs, whether prescriptive orchestration graphs when the models are inferencing in real time, or non-prescriptive agentic graphs which are formed, like where the agent decides what path to traverse. can they be used in the traditional space where there is a lot of feature ingestion happening? There are feature engineering pipelines which you have built, but I think the wait is on to see itself. I think the thing which will simplify this, can LLMs solve that part of the problem? Then you can take the LLM infrastructure as is, even at the upper layers, and start replicating it for Rexis. Until then, I think it's, in fact, majority of our workloads are still Rexis workloads, are not powered by LLMs, right? And
Yeah.
rightly so. They are very targeted, very effective in what they do, and so it's the first hypothesis has to be at the model layer itself. But at the lower layers, we are definitely ensuring that there is standardization across. Like, so it's now the same machine learning pipelines engine which is being used all across LinkedIn, whether it's for Rexis or for LLM workloads, right? So we have standardized all that layer. The topmost layer, when you move towards inferencing and all, some of those changes, we'll figure out as we go. Yeah.
Yeah, where exactly does it divert? Because it is fascinating to think about how the lower levels you've recognized there you can share resources or you can have the same type of stuff going on, but at some point it's diverting right now. So where is that point if you know, or it might be case by case basis?
I think, see, first thing is, so you can look at every single layer, right? Hey, do we need, so for example, when you are going to inference, right? Do you, so people have either written their own inferencing engines, right, in different languages, or you have standardized on something like TF serving from open source, TensorRT from NVIDIA, which were very heavily optimized for models, right, in the Rexis space. When you look at the LLM space, there is VLLM, there is TGI, there is SGLang, right? The inference engine itself, there are custom inference engines being written for LLMs. You just even look at the hardware architecture, we didn't talk about, right? There are a lot of custom chips which are coming. Like, you see many startups, Grok is another example, which are just developing custom hardware for
Cerebrium?
LLMs,
Yeah, yeah,
right?
for sure.
So it's if for people who are investing and taking a bet that, hey, it's much simpler for them because they can just standardize on one, that the one of the reasons, right, where you may feel, hey, NVIDIA GPUs could be better for LLMs, might be if you're right, versus people who are investing in custom ASICs, custom chips, which are potentially, right, uh, um, better for LLMs in terms of inferencing, etc. Is the bet on the architecture. If the transformer architecture is going to replace every single thing, then you can have custom chips. So, right, there is some divergence. Some companies are just going with very custom chips, right, for LLMs. So the engine is different, the chips are different, right? Like, if you build something general purpose, right now we are all standardized. The hardware layer is there is no specific thing apart from the kernel's work, right, which we have been doing, which has been pretty specific. Then you also look at the feature processing infra, right? So a lot of real-time feature processing, feature ingestion, uh, in case the kind of tooling which has emerged in the LLM world, it's, you are talking, LangChain, a LangGraph. Vector DBs are prominent, right? It's not the traditional feature processing, right? And embeddings have become the dominant landscape. And I think we have been on a journey where we are using embeddings all across as well. Started heavily both for Rexis as well as LLMs, but some of the tooling chain there is different, right? What
Yeah.
you will use for something like Beam, for example, for feature processing in the past. Now, a lot of that is happening in the LLM world through the lang chains and the lang graphs, like, when you are actually orchestrating the data. So those are the divergences which are happening and are there for the right reasons. I think, over a period of time, it will reconcile. But yes, that layer is different. When you are handling traditional Rexis versus this, the inferencing engines are different. When you are handling that, in some cases, people are even taking different chips, hardware chips, for these layers. So I think it's bottoms up we have to push. We have to make sure, continue standardizing on bottom layers, right, and go up the stack and see, what else, as we become more mature, what else can be standardized and can be the same. If LLMs start solving Rexes, then potentially maybe, that itself solves a lot of this problem.